Hello everyone, this is Abhishek Mahanti and welcome to lecture number 11 of the chapter Electric Charge and Field. Students, in this lecture I will derive an expression for the electric field due to a uniformly charged finite wire or rod. Students, we have already derived the expression for the electric field due to a uniformly charged infinitely long wire. But today in this lecture we will derive the expression for electric field due to a finite wire which is uniformly charged. So suppose we have a rod whose length is L. This is the rod, and this rod is uniformly charged. This is positively charged, and the length of the rod is L. The length of the rod is L. Is that clear? So this is the case of continuous charge distribution, because charge is continuously distributed over the entire length of the rod. Suppose capital Q is the total charge. Capital Q is the total charge on the rod, and L is the length of the rod. L is the length of the rod. Then we know that the charge per unit length is known as the linear charge density. So lambda means the linear charge density will be how much? Q by L. This is the linear charge density of the rod. We have to find the expression for electric field due to this rod, and we will find the expression at two different points. The first one is at the axial point, the second one is at the equatorial point. So what is axial point? If this is the rod, then this one is the axis of the rod. Is that clear? This is the axis of the rod. And any point on the axis, is known as an axial point. Suppose I will choose a point P here, such that the distance of point P, this is end A, this is end B. Suppose the distance of the point P from the end A is R. Suppose the distance of P from A is R. Then the distance of point P from the end B will be how much? It will be R plus L. It will be R plus L. So now we are going to derive expression for electric field due to this wire at the point P. And since this is the case of continuous charge distribution, we have to follow a procedure. The procedure is, first we have to choose a small element. We have to choose a small element of thickness dx, and suppose the element lies at a distance x from the point P. We have chosen a small element whose thickness is dx, and this element lies at a distance x from the point P, and the charge on this element will be how much? Charge on the element will be how much? dq is equal to lambda into dx. Since lambda is the linear charge density, so lambda into dx will be the amount of charge present on this element. dq is equal to lambda into dx, and this element will behave as a point charge because the element has very small thickness, very negligible thickness. That's why it will behave as a point charge. And you know that for a point charge, the expression for electric field is how much? K. K means the Coulomb's constant, 1 by 4 pi epsilon naught into Q divided by R square or distance square. So now let us write the expression for electric field due to this element. So dE is the electric field at the point P due to the element whose thickness is dx. So dE will be how much? K into the amount of charge present on the element. The amount of charge will be dq, which is lambda into dx, divided by distance square. the distance of the element from the point P is x. So I have to write x square here. Is that clear? So this is the expression for the small amount of electric field at the point P produced by this small element. Now, in order to find the total electric field due to the entire rod, we have to integrate dE. E equal to integration of dE. The limits will be from 0 to E. And what is dE? dE is this much, k lambda dx divided by x square, and here you have to put the limit. What will be the limit here? In this integration, x is the variable. And what is x? X is the distance of the element from the point P. So we have to choose the element on the rod. So A and B are the two end points of the rod. So you can choose element starting from this point up to this point. So the distance of end A from the point P is R. Distance of end B from the point P is R plus L. So whatever element you will choose, that element will lie at a distance between R to R plus L. Between R to R plus L. So the limit of x will be R to R plus L. Is that clear? And in this integration, k lambda is constant quantity. You can take it outside. And here you have x to the power minus 2 dx. The limits are R to R plus L. Is that clear? So next step is E equal to k into lambda. Integration of x to the power minus 2 dx will be x to the power minus 2 plus 1 by minus 2 plus 1, and here the limits are from R to R plus L. That is equal to k into lambda. This one will be minus 1 by x. The limits are R to R plus L, and you can take this negative sign outside. So it will be minus k into lambda 1 by x. The limits are from R to R plus L. This is equal to minus k into lambda. First you have to put the upper limit in place of x, and then you have to put the lower limit. So the upper limit will be R plus L. So it is 1 by R plus L minus 1 by R. And now if you take this negative sign inside the bracket, then the final expression for electric field will be how much? K into lambda whole into 1 by R minus 1 by R plus L. And what is lambda? Lambda is Q by L. So here you can write E is equal to K Q by L whole into 1 by R minus 1 by R plus L. This is the expression for the electric field produced by the entire rod at this point P, where P is the axial point. And now let us derive the electric field due to this finite charged wire, at its equatorial point. Equatorial point means any point which lies on the perpendicular bisector of the rod. Suppose I have a rod of length L, and this rod is uniformly charged, and we have given positive charge to it. Q is the total charge on the rod, L is the length of the rod, and the linear charge density is lambda, which is equal to Q by L. This length is how much? The length is L. Is that clear? And this is the midpoint. Suppose the midpoint is the origin O, then the length of this half and length of this half will be same, that is L by 2. The right end is A, the left end is B. Is that clear? Since we have taken the point O to be origin, so towards right of origin the coordinates will be positive, and towards left of origin the coordinates will be negative. So the coordinate of point A will be plus L by 2 and the coordinate of point B will be minus L by 2. And I have drawn a perpendicular. I have drawn a perpendicular to the rod at its midpoint. So this one is the perpendicular bisector. This line is the perpendicular bisector of the rod. Any point on this perpendicular bisector is known as equatorial point. Is that clear? So I'll choose a point P here. I'll choose a point P here such that the point P is at a distance r from the center O. And we have to find the electric field at this point P. Again, this is the case of continuous charge distribution and we have to follow the same procedure. First, you have to choose a small element on the rod. Let us choose a small element here and suppose the distance of this element from the point O is x. And suppose the thickness of the element is dx. Dx is the thickness of the element. Then what is the charge on that element? The charge on that element will be dq is equal to lambda into dx. And suppose this point is M. We have chosen a small element of thickness dx at point M, which is at a distance x from the center O. And this element carries a positive charge having this value lambda into dx. So what will be the distance of the point P from this element? The distance will be MP, and MP will be how much? R square plus x square square root. This distance MP will be how much? Square root of r square plus x square. Is that clear? Now tell me, now this small element will behave as a point charge. So what will be the electric field due to this element at the point P? Suppose dE1 is the electric field at the point P due to this small element. And since the small element carries a positive charge, the electric field will be directed. The electric field will be directed away from this element. Away from this element. Okay. So this is the direction of dE1 vector. This is the direction of dE1 vector. And what is the magnitude of dE1 vector? The magnitude will be k into charge on the element, which is lambda into dx, divided by mp square, distance square. So mp is square root of r square plus x square. So mp square will be how much? R square plus x square. And the direction is along mp. The direction is along MP. Now I will choose another identical element. Identical element means the second element will have the same thickness as the first element, but the second element will be placed on the left side or on the left half of the center O, and the thickness of this element is same dx, and the distance of this element from the point O is also the same x. Means we have considered two identical elements on both halves of the rod and at the same distance from the center O. Now this element will carry the same charge lambda dx, and the charge is positive charge. Suppose this is point N. Now the distance of the point P from the element N will be same, that is r square plus x square square root. And since this element carries a positive charge, the electric field due to this element will be away from the charge. Suppose this is dE2 vector. dE1 vector is the electric field due to this element at the right side at the point A, and dE2 vector is the electric field produced by the element at N. So what will be the expression for dE2 vector? It will be k into charge on the element, which is lambda dx divided by np square, and this is nothing but r square plus x square, and the direction is along np. The direction is along np. Is that clear? So now we have these two electric fields due to the two elements. Now assume that this angle is theta and this angle is theta. Okay. Now let us resolve the two electric fields dE1 and dE2. If you resolve the two electric fields into its rectangular components, you will get, look, if this angle is theta, then this angle will be theta because they are opposite angles. Similarly, if this angle is theta, then this angle is also theta. They are opposite angles. Is that clear? Now if you resolve dE1 vector, then you will get dE1 cos theta in this direction and dE1 sin theta in this direction. Similarly, if you resolve dE2 vector, you will get dE2 cos theta in this direction and dE2 sin theta in this direction. Now look at the components dE1 sin theta and dE2 sin theta. These two components have equal magnitude but opposite direction, and that's why they will cancel each other, because you can say that dE1 and dE2 have the same magnitude. dE1 and dE2 have the same magnitude, and the magnitude is k lambda dx divided by r square plus x square. So here dE1 sin theta and dE2 sin theta are equal in magnitude but opposite in direction, hence they will cancel each other. So you can see that due to the two elements, the horizontal component or the axial component of electric field is cancelled, but the vertical component, look at the two components dE1 cos theta and dE2 cos theta, they are in the same direction, and that's why they will be added up. So the net electric field due to these two elements at the point P will be how much? It will be dE1 cos theta plus dE2 cos theta. Is that clear? dE1 cos theta plus dE2 cos theta. And since dE1 and dE2 are equal, I can write dE1 here. So you will get dE1 cos theta plus dE1 cos theta, which is 2 dE1 cos theta. That is equal to 2 into, what is dE1? dE1 is k lambda dx divided by r square plus x square into what is cos theta. If this angle is theta, then cos theta will be b by h. b by h means r divided by r square plus x square square root or power half. Is that clear? So this is equal to 2k lambda r into dx divided by r square plus x square power 3 by 2. Here the power is 1 and here the power is half. So when you multiply them, the powers will be added up. So 1 plus half will be 3 by 2. So this is the electric field due to the two elements at the point P. But we have to find the electric field due to the entire wire or entire rod, and for that we have to integrate this quantity, the total electric field. To find the total electric field, you have to integrate this quantity, and here this 2k lambda r, these are the constant quantities, so keep them outside. 2k lambda r integration of dx divided by r square plus x square power 3 by 2. Is that clear? But this type of integration is slightly difficult. Now we'll go to change the variable. Here x is the variable, and now I will change the variable from x to theta. Look at the triangle MOP. In that triangle, tan theta will be how much? P by B, x by r. X by r is tan theta. That implies x equal to r tan theta. So r is a constant quantity, x is a function of theta. If you change theta, then x will change. Then dx by d theta will be how much? It will be r sec square theta, because the derivative of tan theta is sec square theta. So dx by d theta will be this much. That implies dx is equal to r sec square theta d theta. This is the value of dx. Now look at the denominator. We have r square plus x square. That is equal to r square plus, what is x? X is r tan theta. So x square will be r square tan square theta. That is equal to r square whole into 1 plus tan square theta. 1 plus tan square theta is sec square theta. So this will be equal to r square sec square theta. R square plus x square will be r square sec square theta. So in this integration, E equal to 2k lambda r integration of, in place of dx, write this value r sec square theta d theta divided by, in place of r square plus x square power 3 by 2, you can write r square sec square theta power 3 by 2. Is that clear? And here what will be the value of limit? The value of limit will be, look, we are talking about a finite wire rod, especially finite length rod. So the element can be chosen between these two ends. Is that clear? So the limit will be from left end to right end, but since simultaneously I have chosen elements from both the halves, I have already multiplied a 2 here. That's why if I put the limit for 1/2, and since 2 is multiplied here, I will get the total electric field due to the entire rod. So the limit will be chosen for 1/2 of the rod, and since I have already multiplied 2, it will give us the electric field due to the entire wire. So we have to find the limit of theta. So if we are choosing the 1/2 of the rod, then the limit will be from point O to point A. So when the element is chosen at point O, then this line will coincide with this line, and the angle theta becomes 0 degree. Is that clear? When we choose the element at the point O, then this line, means the line MP, will coincide with the line PO. The angle will be 0. So the lower limit will be 0. And when the element is chosen at this point A, then the angle will be this much. And suppose this angle is theta 1. Suppose this angle is theta 1. So you can write theta 1 here. Is that clear? So what will be the value here? R into R is R square. So now I can write that 2k lambda, take this R outside, it will be R square. Then integration of, you have sec square theta d theta divided by, it will be r cube sec cube theta. So you can take this r cube outside, so r square and r cube cancel, you will get r in the denominator, and again sec square theta sec cube theta will cancel, you will get 1 by sec theta here. So you will get E is equal to 2k lambda divided by r into integration of 1 by sec theta d theta, and 1 by sec theta is nothing but cos theta. So you have cos theta d theta. The limits are 0 to theta 1, 0 to theta 1. This is equal to 2k, lambda is q by L, lambda is q by L, and integration of cos theta d theta will be sin theta. The limits are 0 to theta 1. This is equal to 2k q by L r sin theta 1 minus sin 0, sin theta 1 minus sin 0, and sin 0 is 0. So this is equal to 2k q by L r. So sin theta 1 will be how much? If this angle is theta 1, then sin theta 1 will be p by h, p by h. So let me draw this triangle here again. This is R, this is point O, this is point A, and this angle is theta 1. O to A distance is L by 2, this is L. So A to P, this distance will be how much? R square plus L square by 4 square root. The hypotenuse is equal to base square plus perpendicular square square root. So R square plus L square by 4 square root. So sin theta 1 will be how much? P by h, means L by 2 divided by R square plus L square by 4 square root. This is equal to 2kq by L r, L by 2 divided by, here you can take 4 as LCM, you will get 4r square plus L square square root. So finally you will get the expression for the electric field as E equal to 2kq by Lr into L by 2 divided by L square plus 4r square square root divided by square root of 4 will be 2. So 2 and this 2 will cancel, L and L will cancel. So the final expression for electric field will be how much? 2kq divided by R into L square plus 4r square square root. So this is the final expression for the electric field at the equatorial point. So students, in this way you can find the electric field due to a uniformly charged finite wire at its axial point and at its equatorial point. Hopefully you have understood all the derivation, and in the next class I will come with more problems. So till then, bye bye and have a nice day.